Thank you very much for the kind introduction, and also thanks to Dr. Tresco for inviting me to talk in this amazing session. So I'm going to use a theme from last year's ISMRM meeting here. So you heard all these great things about deep learning, and you are maybe excited about it, and now you want to go back home and try this with your own problems, and you may wonder, how do I actually get started? And when you go back, you sit in front of your computer, you want to write the first line of code, or even what program will I start to do this? How do I actually do all of this? And again, using a theme of myself from last year, this talk will not be big wave AI surfing, but it will be really, really practical, hands-on. How do you actually do this, stand up on the board, and actually do this? So what I'm doing is I created a couple of didactic implementation examples, and they will be very, very simple in the beginning and more complex as we progress. And what I actually will do is I will show these on the level of source code. And I cannot do this as a really online interactive tutorial because I don't have internet here, but I have created a GitHub repository with all the data and all the code that I will be showing here. So if you want, you can actually download this right now and go through the examples with me. Maybe the web breaks down, but then you can do it later. And so what I will be covering, I will be talking about software frameworks in the beginning, what you could use, what you might want to use. Talk about generalization, because it was mentioned a lot in the theory talks. So how does it look on a practical level? And this also connects to architectures. So let's start out with software frameworks. Of course, you don't need to use a deep learning software framework. You can program everything from scratch if you want, but they do have their advantages, especially when you think about these sometimes complex looking deep learning models. How do you build those together, right? It might look really intimidating. It looks very, very abstract, very, very high level. How do you do this? So one thing to keep in mind is that all of these deep learning architectures, they are very, very closely linked to this idea of computational graphs. So you can map out, from an implementation point of view, all of these architectures as some kind of computational graph. So you need an architecture or a framework that can deal with a data structure that looks something like this. We want to do numerical computations, not only symbolic stuff, so we need to be able to feed actual numbers in these computational graphs. And because we want to learn our network parameters, we need to get derivatives of our parameters in order to update them during the laning procedure. And also, we probably are going to use quite a lot of data, so we would like to have support to deal with really, really large data sets, and also do high-performance computing, multiple nodes, multiple GPUs, and it would be nice if we do not have to care about all this ourselves and if the framework does it for us. So just to summarize what I think you should look for in a deep learning framework, you want to have some data structures to deal with potentially really, really large computational graphs. You want some automatic calculation of gradients, GPU support, some high-level support to put your architectures together, maybe some data handling functions that you don't have to deal with mini-batches and stochastic methods all by yourself, and maybe some optimizers that you don't have to write all your optimization algorithms by yourself would be nice as well. So just look at, people come up with these rankings, what's really popular based on for example, how many GitHub contributions are there, how often are these referenced on portals like Stack Overflow. And so this is a top 10 of the current, it's actually half a year old, but most popular deep learning frameworks, so let's start there. And when you look at these lists, it's kind of interesting that you see multiple generations of frameworks. So what I would call the first generation of deep learning frameworks are Piano and Caffe, came out of Montreal and the University of Berkeley. And then, like, over, I would say, the last year, 2 years, they evolved the second generation, TensorFlow, PyTorch, MXNet, MCT. And what's kind of interesting when you look at where these are coming from, you probably recognize these. So there has been a transition to industry, so they have really taken these technologies and turned them into very, very powerful software products that you can use. Another one that was on the top 10, which is a little bit of a special case, is Keras. The reason why I mention it separately is because it's actually not a framework, but it is a high-level interface that works with both TensorFlow and Piano to allow you to create your layers in a little bit more abstract way. And I'm going to focus on these in this talk and the examples, pretty much only because these are the ones that I actually use. If you really like one or the other of these companies or plan to use Amazon Web Services a lot, maybe some of the others are better for you. These are the ones I have chosen. But I will also include MATLAB here because I think it is still, especially in our community, so widely used, and I think everybody uses MATLAB, so I will show you how to do deep learning in MATLAB, but also you will see that if you can do it in MATLAB, it's also very, very easy to transition that to a more specialized deep learning framework. The code actually looks very, very similar. So the first example that I made is really, really simple. We are just going to do linear regression, and we're going to look at PyTorch and TensorFlow on a very low level. And these are my input data and my output data points. So it is a very, very complicated problem. You can plot these, and you could solve this just by drawing a single line. You could identify the model you need to learn in order to fit these data. It looks like this. So we are going to do this with PyTorch and TensorFlow because we can. And this is what it looks like on a code level. This is all there is. And you can, as I said, find this in the GitHub repository. And let's look at these individual parts of the code in a bit more detail. So in the beginning, we just define our training data and our model parameters. So in PyTorch, there is this class that's called a torch tensor. And you use this like you would use a variable or a matrix in MATLAB. And there is one interesting feature here. Remember, we talked about automatic differentiation when we do backpropagation. For our model parameters, we can simply add these little flags here that says we require the gradient, and that tells PyTorch we want to have the gradient, and we will be automatically able to get the gradients of these parameters during our training. Then we define our model. So it's just a simple linear model with 2 parameters. And we define a loss function. It's just a mean squared error that we want to minimize. And then we are actually going to loop over our training examples. So let's look at that in a little bit more detail. It's completely ridiculous that I use stochastic method and mini batches for my 5 data points that I have. But yeah, I did it because we can do it. And then the actual training procedure is actually very, very simple. You just do the forward pass of your data through the computational graph. These are your data patches and your labels. Evaluating this passes the data through the networks, gives you the loss. Then you do the backward pass to update your model parameters. You get the gradients. And if you remember, we said for our model parameters, we want to have the gradients there. And they are in this data structure. And we can just do a gradient update step to update our model parameters, and that's it. We have done our training procedure. And then we just loop over this. And there's one particular thing that's specific about PyTorch, and that this computational graph is actually dynamically created during these iterations. I don't have time to really go into technicalities of dynamic and static graphs, but it is a distinction of PyTorch against TensorFlow, and it explains why the TensorFlow code looks how it looks and how the PyTorch code looks how it looks. So that is just something to keep in mind when you're puzzled at maybe how does this look like, especially for TensorFlow. So let's look at the actual results. I mean, this is a super easy problem. It converges super fast. We get down to almost zero loss. And when we plot our model parameters as we expect, we actually converge to the exact parameters that we know the model needs to look like. Also, we didn't add noise or anything, so this is a super simplified example, but it illustrates how you can do something like this in a framework like PyTorch. So one thing I mentioned, GPUs, it is very, very easy. So this is an example that runs on the CPU. If you want to do the same thing on the GPU, you just define your torch tensors to be on the GPU, and this is all you have to change. Now it runs on the GPU. So let's look how it looks like in TensorFlow. The difference that I mentioned is that TensorFlow uses what's called a static computational graph. So you build the graph once in the beginning, and then during the training procedure, it cannot change anymore. And that is a reason why we have this somewhat weird appearance that our training data is actually just NumPy arrays, that they are not TensorFlow variables. They live outside TensorFlow. But our model parameters are TensorFlow variables, and then we have to create what's called placeholder variables that tell TensorFlow, you will get this data when we actually train, but the data doesn't exist yet. So, or the memory allocation and everything, from the point of TensorFlow, this data isn't there yet. So and that makes TensorFlow code maybe look a little bit tricky when you first look at it. Then we just define our loss again, and also I have decided to just use an inbuilt optimizer of gradient descent or from TensorFlow instead of writing gradient descent ourselves. We could have done it as well, but we can also do it like this. So then we just loop over our training examples again, and here I didn't bother with mini batches anymore because it's just too ridiculous for these 5 data points, and no, I don't have a zoom there. So we just loop over the examples, run a session of this computational graph, and then do an update of our optimizer, and this updates our parameters, and that's all that is. Again, the results, as you probably would expect, you get the exact same result with TensorFlow that you had with PyTorch, and they are pretty much equivalent in terms of training time and everything for this example. So let's move to an example that's a little bit more interesting. So we're going to do a classification of brain tissue from DTI data from the Human Connectome project, and this will allow us to take a first look at high-level modules to build neural networks that are a little bit more complicated than this simple linear classifier or regression function that we had before. So this is the data or the example we are going to use. We have a segmentation and T1 weighted and diffusion data of the brain. I have selected 3 anatomical structures, the corpus callosum, some subcortical white matter, and the thalamus. And we have the following data: T1 weighted, FA, mean diffusivity, axial diffusivity, and radial diffusivity. And we are going to classify which category of tissue does our voxel belong based on these 5 pixel values of an individual voxel. So this is how our data looks like. We have a feature vector with 5 entries, very, very simple. And then our class labels. So let's take a look at how this looks. And one thing you immediately notice is that these feature points live in very, very different numerical scales. So what you want to do is you want to normalize them to the same range to speed up the training and make everything run smoothly. I decided to normalize everything between 0 and 1. What's commonly done with people working with images is zero mean and unit variance. So you will see that a lot. So just something to keep in mind if you use your own data, look at the numerical values that you're actually dealing with. And then I split the data, this is what everybody does, in a training set, a validation set, and a separate test set. And as the name says, you want to use the training set to actually train your model. You want to use the validation set as your performance criterion as you make your design choices, change your architecture, do hyperparameter tuning, whatever. And the test set you really don't want to touch during training at all. And it's probably the best case that you don't even see it during all your development. And then only when you deploy it, that's when you see how well your model really generalizes on the test set. So what I did here was I split it up. I used 80% of randomized samples from 3 subjects for training, the remaining 20% from these 3 subjects for validation, and then a different subject as the test set. And in terms of actual number of data points, so it's a bit more than 20,000 data points, and this is how they are split up into their individual categories. And then one thing you always should check is how well balanced are your classes. So for this example here, the thalamus is a much larger anatomically area than this small part of the corpus callosum I selected. So it has a lot more voxels. So that means I have a lot more data points for thalamus or for gray matter. And that is something to keep in mind. It's not, so this data set is not as critically unbalanced so that I would be really, really scared and think crazy about what do I need to do to balance this. If you are dealing with very, like pattern recognition for very, very rare diseases where you have a very, very small number of samples, then there are some tricks you can do. The easiest one is you can just create duplicates of your data, but there are more advanced strategies. So if you are dealing with problems that look like this, there's a very nice overview paper that describes strategies. But just check the balancing of your classes. So let's actually build our very, very first neural network. It's a multi-layer perceptron. Daniel has shown how they work in the previous talk. We have an input layer. We have 3 hidden layers with 100 elements. An output layer. We use ReLUs as the nonlinearity and some softmax output. And this is how it looks like. This is our input feature vector with our data and our output classes. And when you take a look at the number of parameters, this has more than 30,000 parameters. So this is not a toy model anymore, like our linear line that we learned in the first example. And now let's build it for real in these different software frameworks that we have available. So let's start with MATLAB. There we're going to use the neural networks toolbox. For PyTorch, they have a corresponding neural networks package, and for TensorFlow, we're going to use Keras. So this is how it looks like in MATLAB, and as you can see, you can actually operate on a very, very high level. It's very intuitive. You just define your layers, fully connected layers, the number of elements you want to use, put them together in your architecture the way you need to design it. How many epochs do you want to train, what's the mini batch size, learning rate, and then you just select an optimizer. I used Adam here. You can decide, do you want to run it on the CPU or on the GPU? So MATLAB actually does allow you to run your code on the GPU, and it actually works pretty well. It's, I was surprised how efficient it is. And then there's just a one-liner. You train your network, and you're done. So that's very simple, right? Yeah. Let's do the same thing in PyTorch. And as you can see, it isn't actually more complicated. You have your networks module here, and you just do the same thing that you did in MATLAB. You just stack your layers on top of each other, linear layer, ReLU, whatever, a number of elements. That's your model you're going to use. Then we have our hyperparameters, data loading, helper functions. And then there's the actual loop over our training data where we adjust the parameters of our model, and this looks pretty much the same as it looked like for the linear regression example that we had in the beginning. So we do a forward pass of our data, get the loss function, do a backward pass. This goes in the optimizer function. We update our parameters, and we loop over this. We're done. Same thing in TensorFlow. And this is now the interface with Keras. So we have this high-level view. Again, we just add our dense layers, how they call it in Keras, put our model together. Then there is this functionality that Keras provides. It's called Model Combine. This essentially builds your computational graph, puts your model together, tells TensorFlow that's below Keras what optimizer to use, what loss function it should use, and oops, yeah. And then it's a single line. It's you fit your data to your model, and you're done. So this is for the example that I have shown, and for this particular data is the result you get with exactly this architecture. This is the PyTorch result, but they're pretty much all identical. We get reasonable accuracy, a bit more than 80%. It generalizes pretty well on the validation set and also on the test set. So I was happy with that, and maybe you are not. So things you could do, since this already generalizes really well, maybe you can use, if you want to experiment with this yourself when you look at the repository, maybe you want to use some higher model complexity. A good thing to do is always take a look at some examples of your data that were wrongly classified. You might find some patterns. For example, the classification example here, obviously it will be a lot easier to separate white matter from gray matter than to separate the two white matter structures with more or less aligned fibers. So maybe you can find trends there, and this allows you to think a little bit about your features. But whatever you do, don't use your test data at all. Don't touch it, because then you will have broken this independence of your test set. Use your validation set. It's really important. And in the last example, we're actually going to move to convolutional neural networks, which I think most people will probably be interested in. And what we're going to do is we're going to build a classifier that tells us if our images have good image quality or not. So this is an example of the data. So this is accelerated parallel imaging reconstruction, parallel imaging compressed sensing reconstruction. And as you can see in this example here, sometimes it's really, really easy to distinguish between those two because our reconstruction wasn't particularly good. We have lots of residual aliasing artifacts. But sometimes you can see that our images have this slightly blocky, artificial-looking appearance that you often have with compressed sensing. So you can still distinguish them, but you can see it gets a little bit trickier. Sometimes you only use small features, small details, like these bone trabecular here. They're pretty much lost in the compressed sensing reconstruction. But sometimes they're actually pretty darn good. And so now the problem becomes, so now if you ask me, can you describe me a model that separates between those two images, just some linear classifier or whatever, yeah, I'm lost. And actually this is, if you are more interested in this separating between reconstructed images, this was part of our early work about generative adversarial strategies for image reconstruction and combining learning this feature classification with image reconstruction. We will have a talk, Kerstin actually will present it this Thursday, so if you're interested in that. So yeah, let's do our experiment. So what I did here in the repository example, I separated the data into 2/3 for training, 1/3 for validation. And so there's no test set here, so if you want to do this, please do the experiment. So you might learn something. And this is a pretty small data set just for didactic reasons, because you can actually show some interesting properties in this example. So these are the numbers of the data set. On the good side is that they are completely balanced. We can just take the same data, we have the reference, and we have our compressed sensing reconstruction, so we don't have to worry about that. So let's build our first convolutional neural network. It looks very similar to what Daniel has shown you before. We have a couple of convolutional layers with these parameters, kept the same filter sizes and numbers of filters. We do max pooling, and then we have a fully connected layer at the end, and a sigmoid output. So we have a binary classification problem. We have a bit more than 25,000 parameters. So let's see how that looks like. And I have used TensorFlow for this example. Very, very straightforward. Again, you just build this together, conv layer, max pool, conv, max pool, conv, max pool, and this is our fully connected layer down there. You will see what that is as I go through these examples. And then TensorFlow has this nice visualization tool called TensorBoard. This is how our computational graph actually looks like on the level of TensorFlow. This is a nice debugging feature in case your model doesn't work or doesn't do what you want. You can look in there, see have you actually built it correct. And let's train this. This is our result, like 100% correct. Like, hooray. Does work great, right? Except it doesn't. So we have really used a much too complex model. We have severely overfit the data. We have no generalization. Our error on the validation set is horrible. Okay, we have learned something. Let's use a much simpler model. Just one convolutional layer, and let's get rid of the fully connected layer by using just pooling. It's similar to what Daniel has described before. Essentially, you say, I don't need a fully connected classifier in the end because my convolutional layers have already transformed my data in a feature space where they are trivially to separate. So I'm just going to average up over all the output of my less convolutional layer and do a thresholding. And suddenly we only have 45 parameters. Super simple model. Well, unfortunately now that is our performance. So now we cannot even separate our training data anymore, and it doesn't particularly help us that it generalizes well because it's useless. But this is a very, very simple and an experiment that you can do always at the beginning when you work with a new data set. Take a small subset of your data and see if you can completely overfit it and underfit it. So, because if you cannot overfit it, that means that there is something really, really wrong, either with your architecture, your data, or your optimizer. So maybe you have a bug somewhere. So you have to be able to overfit a small subset of your data with a model. Okay, but let's try to use something, do something useful. Let's look at how our parameters are actually distributed in our first model. So we had these convolutional layers, and we had the fully connected layer at the end. So we have a pretty reasonably small sized number of parameters in our convolutional layers, a little bit more in the later layers because we have 4 feature like the dimensionality of a feature space is 4 because we have used that number of filters, also like Daniel described it before. But then we have more than 25,000 parameters in our fully connected layer. So that means almost like more than 98% of our parameters are there. So let's just replace the last convolutional layer with max pooling, global average pooling again, and we have suddenly dramatically reduced the number of parameters. It's less than 500, And many modern network architectures use this strategy, the Google Inception model, modern ResNet models. And this is actually one of the reasons why, even though these modern network architectures that you have seen that look very, very complex, they use a lot less parameters. And that helps with generalization, with training them. So that's a nice trick you can use, or you can try out if your data works. With this. So let's train it again. We also get pretty close to 100% accuracy there, but now the big difference is it actually generalizes really, really well. So if you want to take this from I left it in the repository, things you can do is you could use a separate test set. Again, look at your misclassified samples. There were some in there that actually looked a lot closer to the reference than others. You can experiment with the architecture, number of conf layers, filter size, or something I didn't touch upon, you could actually use a higher model complexity, but combine it with regularization, for example, using dropout. So to sum up, we walked through a couple of examples of how you actually do deep learning yourself. We looked at software frameworks. We did a pretty high-level view on generalization, model complexity, overfitting, underfitting. If you are more interested in this, especially in the context of image reconstruction, we have an e-poster that discusses this in pretty substantial detail on Monday. And yeah, we also looked at convolutional, fully connected layers and the associated model parameters. There are a couple of upcoming workshops and events. If you are interested in this, just wanted to point them out to you. And finally, as a parting statement, remember that machine learning really solves the problems that the world really cares about. So this is a paper that came out last week. So this is, according to machine learning, Germany will win the World Cup. So the doubters here is Jeff. Yeah, so if Germany wins the World Cup, then thank you.